So good morning, everyone. My name is Festa Ndubuogaranya. I'm currently a first year PhD student at the University of Lagos. So for today, I'm going to be presenting my MSc thesis, which is on neural ODEs for parameter estimation and simulation of some selected prevalent diseases model in Africa. So for this particular study, I worked on four selected diseases, which are HIV/AIDS, COVID-19, malaria, and tuberculosis. So I'm going to take us through the aims and objective of this study. So first, we try to analyze existing neural ODE models and algorithm for modeling the spread of infectious diseases. So afterwards, we built a neural ODE model for the particular diseases we are working on. So we worked with numerical informed data for tuberculosis and HIV/AIDS, and we actually worked with a real life data from Benue State, which is for malaria, and then for the COVID-19 data, we worked with the general Nigerian data. So afterwards, we visualized the future trends of the spread of each diseases. Now, we started with a simple model, which is the SIR model, to see if the network is actually going to, if the neural network, which is what we use in learning the trend of the diseases, if it's actually going to capture the trends before we now move forward to actually work with the four diseases we are trying to look at. So for the numerical simulation, that's for the diseases that has no real time data, which is the HIV/AIDS and tuberculosis. We use the classical fourth order Runge-Kutta method to actually simulate and get data before we now use the neural ODEs to train this data. Okay, so this is what the neural network look like of the neural ODE model. So first we can see at this particular place we have the input layer. So for the input layer, the network takes in the time and the compartment of the disease. Like I said, we tested with SIL first. Then if the model, if the neural network is actually able to capture the trend, now move forward to work with the disease data the diseases we are trying to model. So for the input layer, it takes in the time and the S compartment, I compartment, and the R compartment. So these are actually values with respect to time. So for this particular study, I worked with eight hidden layers, and each layer has 20 neurons. But this is just an example, an illustration I want us to just see. So we'll see what the diagram looks like. So for the this particular one is showing us that we have three hidden layers, and each layer has six neurons. Then for the output layer, it gives us the prediction of this particular of the compartment of the diseases. So here we have the S hat, I hat, and R hat, which represents the prediction of the model. So this is what the architecture of the neural networks look like. So for this particular study, I used the Python programming language to build the neural network. That's the model of the neural network. So for the architecture of what it looks like, the first thing we did was to, yeah, I for this study, I didn't design my model, that's the disease model. So we worked with already existing disease model from existing literatures. So which are the compartmental model. Then afterwards, the architecture of the neural network, the first thing is to load the data. So which is the real-time data I talked about. And for the tuberculosis and HIV/AIDS, which is we use numerical data. So afterwards, we define what the network should look like. Then we normalize the compartment of this data, and we try to optimize the neural network. And for optimizing the neural network, we look for the gradient of each compartment. We unnormalize. So when I talk about normalization of data, I'm saying like when for disease data, for instance, if we're working with SIL, the S compartment, which is for the susceptible class, we know it's kind of like it's related to the total population of a particular region. So say we have, for instance, in a particular region we have 10,000 population. So the susceptible class will actually be maybe the 10,000 until when they start getting infected before the population reduces. So if we're trying to work with something like that, and where the infected class maybe will have just five individuals, and maybe recovered class we have just, let's say, three. So if I'm trying to train with such data, the susceptible class is going to dominate the training because it has large numbers. So we try to normalize so it be in the range of 0 and 1, so that the network can actually capture the trend of each compartment without a particular compartment dominating the training process. Then for training the network, we try to work with a loss function and an optimizer. For this study, we worked with an Adam optimizer, and for the loss function, we use the mean squared error. So For the okay, I'm going to talk about the epoch with time. So now this is the for the numerical informed approach, which is where we use the fourth order Runge-Kutta method. So for the HIV/AIDS, it is divided into four compartments, which is the susceptible, infected, pre-AIDS patients, and the AIDS patients. So this particular model was gotten from Kibona et al. In 2011, which he formulated the following systems of ODE. So we have this system. So I'll show us the schematic diagram of the system. So this is what the schematic diagram is for the HIV model. Then afterwards, we worked with the parameters he listed in his study. So the parameter he listed in the study are this particular one, which I wrote the actual value. So with this actual value, within the network does not know, as it does not, how do I explain it? So the purpose of this study is for the neural network to be able to estimate these parameters. So the actual parameters, I got them from the literature, but the only time we used this was to simulate using the fourth order Runge-Kutta method so that we can get data. So now when it's now the time for the network to train and learn from this data, the parameters were not known to the network. So this is what the network estimated. So here we have the estimated parameter. So after learning from the data, that's from the HIV data, which I estimated, which I simulated using the fourth order Runge-Kutta method. So after learning from this data, the neural network was able to capture this particular value. And let's look at the first one, which is the Q. So which is a recruitment rate. So we have 2,000 for the actual value which I got from the literature. So the neural network was able to capture, was able to predict or estimate 2,000.44. So we can see it's very close. If you look at the relative error, which is in percentage, we have 0.0222. So meaning that the network was actually able to like not really give us the actual value, like the exact figure, but it was able to predict something very, very close with minimal error. So we can actually look at another one, which is alpha. For the actual value from the literature, we'll have one. The network was able to capture 1.00094003. So it's a relative error of 0.094, which is also in percentage. So now this is the loss during the training process. Like I said, we predicted the loss or calculated the loss using the mean squared error. So then this is the prediction of the HIV model. So the dashed lines, let me zoom this so we'll see it very well. So this is what the prediction looks like. So the dashed line, such as in is showing the prediction, that means what the network predicted after learning from the actual data. Then the solid line is what we have, like what the data looks like, the real-time data we simulated using the fourth order Runge-Kutta method. So the solid line represents that. Then after the network learns from this data, it was able to predict what we have in the dashed line. So we can see that the network was actually able to learn from this data and predicted exactly what we have there. Though the error is actually we've actually calculated the loss, so we see what the error looks like. The error is actually very minimal. So from this diagram, we can see the network was able to capture the trend of the diseases. Then afterwards, we did a future forecasting, which is trying to predict what the next 15 years is going to be like. So for the original data, we worked with 35 years over as in time frame. Then the network predicted the next 15 years. So, but for because this is not a real-time data, we can't use this prediction or this forecasting for any valuable, like for any purpose. We're just trying to see if the network can actually do something when it comes to predicting what the next few years or few months is going to be for the diseases and for the disease in a particular region. So afterwards, so now we actually move to the data-driven approach. So just like I mentioned that for the numerical approach, we worked with HIV, AIDS, and tuberculosis. But for just for this purpose, I'm not going to be talking about the tuberculosis because it's also the process I took for the HIV, AIDS that I also took for the tuberculosis. Now this is for the data-driven approach. So I mentioned we worked on COVID-19 and malaria, but for this slide, we're going to be talking about only the malaria. So the spread of malaria involves two different species of which is the human and the vector population. So for the human population, the compartments we worked with is XIR, and for the vector, we worked with susceptible and infected. So this particular dynamics of the spread of malaria, the system of ODE was gotten from Rajrayan and Kumar 2024. So this is from an existing literature from last year. So this is what the dynamics look like, and this is the schematic diagram. So we have the recruitment rate, which goes into the susceptible class, and this is the natural death. Yeah, this is natural there, and this is the transmission from S to I. So this is what the flow of the malaria model looks like from Kuma and Rajayan 2024. So for this particular one, we worked with a real-time data from Benue State, Nigeria. So this particular one, we don't know, and from data, we can't tell the parameters from ODEs, like from the system of ODEs we have above. We can't tell the parameter. So now this is where the main work comes in for the neural network. So since it was able to capture, like predict with HIV/AIDS, this is what is predicted, this is the error and all that. But for this particular case, we don't have actual parameters from the real life data we worked with. So the network was able to capture this using the system of ODEs we gave it. So for gamma age, it's predicted 0.0137736. For beta age, it's predicted this, and so on and so forth. So this is the loss it actually undergo during the training process, and this is the prediction. So I'm going to zoom this so I can talk about each compartment. Okay, so this is susceptible human population. So from the actual data, the real-time data, this is what the class looks like. Like it goes as in linearly, it increases. So this is a linear increment. Then this susceptible human prediction, this is the dashed line. So for the prediction, so for the prediction, we can see the network was actually able to capture the trend perfectly. It was able to, like, let's not use perfectly, because let's say closely, it was able to capture the trend of this susceptible class. Then we'll go to the infected class. So we can see there's this trend from the infected class of the real-time data. The solid pink line represents the actual data, and the dashed line represents what the network predicted. So though it's not, it didn't capture, like it's captured from the beginning. Let's take it from, so this is a month, so it's captured from zero up to the 10th month, and then it was able to follow the trend, then continued with continue with the trend up to the 40th month. So, but one thing about neural network is that the more it trains on a particular data, the more it learns. So it's just like the human brain, that when you teach a baby something, over time they get to master that thing after continuous practice. So after continuous practice with this neural network, I did this work last year. So I was able to train the data again, using as in train the network again using the same disease data, and it was able to capture better than this. But though it's not in this slide, like I said, this is my MSc research. So but I was able to show it to my supervisor, and we were able to see that the network has actually learned better over time. So, but this is what we have for now. But just so you know, the network captured even better trend than this. So meaning very, very close. So meaning the error is actually going to be minimal. Then we also have for the recovered class also, and we have for the successful mosquito. So for the successful mosquito, we can see what the trend looks like. It's also very, very close. And afterward, we have the infected mosquito also. So So this is just for the prediction, and we also have for the forecasting. So we try to forecast the next. Okay. I think I see what happened here. So for this particular one, we worked with, let's see how many thousand epoch. I didn't mention that, but I think this should be like 150,000 epoch. But I had to increase the number of epoch. So epoch means like the iteration time. So I tried to increase the iteration time up to 100 and okay, this is 1.5 million epoch, and the network even captured the better trend compared to what we have here. I think this should be either 150,000 or 300. I can't really give the figure, but here I stated it is 1.5 million. So the network even captured better trend here. So it was able to capture like the peak, the trend, and every movement of the actual disease data. So just like I mentioned earlier, I was able to train the network again this year, but I didn't work with 1.5 million people. I think I maintained the 300,000 or 150 or thereabouts, and the network learns better. So the reason for not trying to use 1.5 million is that if the larger the number of people, the more time the network trains. So for this particular study, I think this 1.5 million took me 4 hours for the network to be able to train and give me the predictions I want. So, but for 300,000, that should be like 16 to 40 minutes or thereabouts. No, I think it's not up to 40 minutes. Let's say 15 minutes or thereabouts. So, the more the network learns, the better, because you're not going to spend so much time trying to do prediction. Like this took me 4 hours in a place where there is no electricity, and maybe the computer cannot actually stay up to 4 hours. That means a training cannot actually go on, and we cannot undergo training using the neural network. So that's that. And so this is me trying to predict the future trend of the network. So I think I predicted the next 10 months. Since the actual data has 40 months, I predicted the next 10 months up to the 50th month. So this is what I have for my future predictions. And so we try to have some discussion from of the results we have above. So for the HIV/AIDS, which is where we use the numerical approach, it says we generated 200 data points from year 1 to 35 for the CPA model with known parameters. Like I mentioned earlier, these parameters were provided using the literature from Kibona et al. 2011. So we use it to solve, and we use the fourth order ROK method to solve the CPA ODEs using the parameters we got from this literature. So the neural network computed for the CPA model has 8 fully connected hidden layers. I mentioned that earlier. For this study, the whole training we did for the neural network, we maintained 8 hidden layers and 20 neurons for each of these layers. So with the learning rate for HIV/AIDS, the learning rate we used was 1 times 10 raised to the power minus 5. So the model was trained for 100,000 epoch, about 19 minutes. So I mentioned the lesser the number of epoch, the lesser time. The larger the epoch, the larger time. So this is the relative error I got for the 4 compartments. That's comparing the actual data to the predicted data. So this is the error for the S compartment, the I compartment, the P compartment, and the A compartment. So the trained neural network estimated the learnable parameters. So figure 3, I showed us the loss in the training process, and I also showed us figure 4 and table 1, which shows the visualization of the predicted outcomes and the estimated parameters. So this is for malaria. So we use a real life data on the monthly incidence of malaria in Benue State, collected from the Benue State Ministry of Health. So we got permission from Adeni Etel 2023 to be able to use that, because he also used that in his work. Then the neural network computed for the SIR-SI model has 8 fully connected hidden layers. So I mentioned we are maintaining that, but the learning rate for this one is 1 times 10 raised to the power minus 9, and the model was trained. Oh, I made mention of 150, 300, but the model was trained for 100,000 people at about 15 minutes. So this is the relative error we got. Then the neural network estimates the learnable parameters I showed us in figure 7. Then figure 8 to 12 showed us the visualization of the predicted outcome. Now, increasing the number of people for the malaria model, we increased it to 1.5 million, and this particular one took us 4 hours, 2 minutes, 14 seconds. And I showed us the visualization of that prediction and also for the future prediction. So these are my selected references for this work. Thank you.
Yeah, thank you very much, Ms. Festa, for your wonderful presentation. Yeah, the only challenge I had was that I think your internet was very slow. So while you were moving your
Oh,
slides, it was lagging, so we couldn't follow your slides. But I want to thank you for helping us to cover up for the absence of our lecturer today. Maybe I'll just entertain maybe 2 or 3 questions to Miss Festa. Any question for Miss Festa? Comments, question?
Hello, Professor.
Yes, please go
A,
ahead. Please go
a
ahead.
friend of mine have a question, so he wants
Yes,
to speak.
please let him go ahead.
Hello, Professor. Hello, everyone.
Yeah.
hello.
Um, Thank you, Festa, for your presentation. I'm actually interested in the area of the application of AI to the epidemiology of diseases. And so I just wanted to ask, aside using neural networks to estimate the parameters, what other applications can um, AI be applied to for the epidemiology of diseases?
Okay, aside prediction of data, prediction of parameters, what other application? So I think I mentioned one of the application, which is to forecast. Because if we are working on the spread of disease, it's actually going to be great if we can tell what the spread of that disease will be like, so that we can know the control measures to actually apply to curb the spread or the outbreak of these diseases. So I think when it comes to forecasting, like probably I won't suggest forecasting for a very wide period of time, because it might not be able to give us, as in, like, give us what we are expecting. So probably we should capture like next few months, or probably the next 12 months, to see what the spread of a particular disease will be like. So I think in the area of forecasting, an application of neural network should be applied there, or AI should be applied there.
All
Okay,
right,
thank
thank you
you.
very much.
Yeah, any other question?
So I also have a question.
Yes,
Thank you
please.
for the presentation. So my question is it possible to also apply this neural network to determine the growth of tumor in the case of cancer? You know, when we talk about cancer, genetics, and all of these things, and you're talking about simulation and forecasting, and we know in most cases about cancer is about tumor and the growth. If it's possible for us to use this neural network to simulate and forecast
Yeah,
um
yeah.
you know,
I've
and
not worked on tumor before, but from my knowledge of neural network, I believe it should, because I've actually tried to use neural network using the PyTorch library. Yeah, this I actually did this work using the PyTorch library also. So to actually, do some simulation with heat equations and probably like some other things. And I've actually also worked on temperature also, using the same neural network to forecast like what the temperature or the weather forecast of a particular region is going to be for a period of time. So I think it should do that. I think it should.
Yeah,
thank
and to add to that, if your model, that the model that describes the growth of the tumor is a differential equation,
Yeah.
then you can apply the neural ODEs.
okay.
Yeah.
Yeah.
That's
Thank you, Professor. Thank you, Festa.
Yeah. Any question? Any other
true.
question?
Sorry, can you please drop your email address, Festa, so we can probably
Okay.
In
communicate
the
through
chat,
that.
yes, chat box.
All right, I'll do that now.
Any other question? Okay. In the absence of no question, I think we have done very well today. Hopefully, September edition will be very, very smooth, and we see you in September. Thank you for coming.
Thank
Thank
you.
you, Prof.
Yeah, bye-bye.
Bye.
Bye, yeah.
Thank you for having us.
Yeah, bye-bye.